Good morning and welcome to our presentation. So we're going to be talking about debugging of flash issues observed in hyperscale environment, Meta being one of the hyperscalers. In there, we'll talk about some of the problems and challenges which we face. We will also share actually a case study of how we have debugged one of the most challenging issues we have seen at Fleet and how at scale basically this problem gets amplified. Myself, Vineet, I work as a hardware systems engineer at Meta. Part of my responsibility is to design and maintain storage at Fleet at Meta. My co-presenter here is going to be Venkat, who is part of the same team working as a hardware engineer in storage. So a little bit about scale. Once I joined Meta, I had learned a lot about what at scale is and heard that it means a lot of devices, a number of devices, but you really don't experience it until you actually kind of dive and put your hands dirty inside the scale. So the scale, what we're talking about, like our family of apps has around 3.95 billion users per month, active users in there. If you try to map this across, billions of requests which are generated to the hardware systems means thousands and thousands of SSDs which are accessing either through reads or through writes every second. So that's the scale what we are talking about here. To give you a little bit about high-level failure overview, and I'm going to dive much deeper into how we have designed our systems in terms of how do we monitor our drives in our fleet, what type of mechanisms we have put in place in terms of the data we look at the flash drives, and that's always getting updated, and we are trying to add more and more data to better understand how the drives perform at scale in our environment. A high-level overview of this is once we deploy the drives, we have these three big buckets which we actually fire off on every system of every drive which exists in the Meta infrastructure. One is monitoring, and we'll dive a little bit into monitor in terms of what we monitor, what data we look at, and as I said, that's continuously evolving as we learn more and more about SSDs and we add more features into it. A second is alerting. One of the challenges you bring with monitoring is when you're looking at thousands and millions of devices which are across the fleet, you can't really babysit and monitor each and every SSDs and try to be, kind of read failure mechanisms on a particular set of systems or on a particular set of tiers. You really need good alerting so that you can find hotspots, you can find anomalies, so that you can kind of do all of this in a more tool-mannered way and a more optimized way versus actually a lot of manual work. And that's where anomaly detection comes. So we do a lot of post-processing on the data, which is generated from monitoring and alerts so that we can find anomalies and we can find issues happening in a fleet. An example of that could be if a certain model with a certain firmware, with a certain kernel version is actually causing a bad behavior, then that's something what we try to identify and see that, okay, this combination of these four is actually causing a lot of our problems in our fleet in there. So that's where a lot of anomaly detection comes. The output of all of this goes into triage. So that's where some human is probably looking at it and trying to understand once a problem is detected, why this is a problem, working with the vendors, the flash vendors, and trying to understand even more in terms of what we can do to kind of go and remediate and solve this problem. And then again, a review, which is we want to make sure that this problem is fixed in the next generation of the SSDs, and even if and sometimes what happens is when we face this problem, we would find 10 or 20 SSDs which are actually going and exhibiting this problem. And while we are doing all of this triage, we need to figure out what are we going to do about the other thousands of those which exist in the fleet. We have to take actions and remediations if there is actually going to be a service impact on those SSDs. And so a review step basically helps us in coming up with what are we going to do in the meantime till we actually go ahead and find the actual resolution of the particular issue. But we'll dive into this more in depth. So I talked about some of the monitoring and data collection aspect. So I've broken down the data collection here in two different buckets here. One is a periodic collection, which we do at scale. It's completely automated in nature, and there is a non-periodic. The periodic one is, it is dependent on the vendor and the model implementing some of these log structure, and is pretty efficiently captured by automation. The non-periodic ones is something I really hate, and I would love us to kind of go away from the model, but that's where the storage industry is at, and we're trying to influence in that area so that we go away from this model, because it requires us to pull some of these telemetry logs and the drive event logs. Most of the flash vendors out there, you might understand, these drive event logs are pretty big. They take a lot of time, and we cannot always keep pulling these logs on a periodic basis. So you really need to know when you want to pull these logs for the flash vendors to go debug these issues. Some of the things which happens automated is like we capture all the smart attributes, the demessage logs. Then we have the OCP cloud spec, cloud health log page, which is defined in the OCP spec. There are a lot of interesting statistics which are defined in there. We capture them as well. And then we have the new addition called as the latency monitoring log, which got added to the OCP, which we basically pull and save it to. This happens multiple times in a day on every single SSD which exists in the Facebook infrastructure and gets saved in our database. So for us to then post-process and analyze how the drives behave in our fleet, and sometimes also help vendors for them to understand how their drives are behaving in our fleet, so far we can design better next generation drives and solve issues and stuff like that. Okay, so now let's talk about how does all of this data which we are getting collected and the overview I kind of presented happen at scale. So we have a daemon which basically runs on the machine. So you can think about this daemon, as a script or as a Python module or as a piece of code which gets run on every single hardware machine which exists in our infrastructure. This daemon basically calls something we call as the machine checker. This runs periodically. There is a time set where this just wakes up and it just basically goes and runs there. This machine checker has a lot of checks which are defined to go check every hardware component which exists onto that system. So it could be the CPU, could be the NIC, could be OS and kernel through system event logs and through demessage, and then SMART through SSD. So if you go back in here, like all these attributes which I talked about here, which we periodically collect, we could come up with certain machine checker checks in terms of how we want to do storage. We don't really publish it in open, all the checks what we defined over here, but one of the most interesting and the simple one is like the critical warning. So if let's say a smart critical warning of an SSD went high, that means the SSD is actually in a faulty state. We don't want that drive in the production. We want to take it out because it's going to impact production. This daemon would actually go find that through its smart attributes and it'll pull the drive out as soon as it saw that happening in there. So once a machine checker basically finds a particular faulty device based on the check criteria which is defined for it, it then goes ahead and alerts something we call as FBAR. So the full form there is like Facebook Auto Remediation. We haven't updated it to Meta Auto Remediation yet, but maybe we need to change that name. It picks up the hardware failures and processes the log information, and then we have custom remediation which is designed for every check. So it doesn't mean that if we actually go ahead and find a particular failure in machine check, we're just going to take the drive and throw it out probably in there. There are many remediation techniques which we have designed depending upon the type of failure which we might process. And so the remediation from a flash drive perspective could be just rebooting the system, or it could be hot swapping the drive, or it could be formatting the drive, it could be sometimes firmware updating the drive. There are all sorts of remediation which you can think of which are deployed depending upon the type of check and failure which you do. And this is all tool defined, so there's no human which is looking at it. Once we define and put it out on the tool, it gets applied to every drive or every SSD which exists in the Meta infrastructure. So once FBAR basically goes and fixes it, we have Cyborg basically kicks in. So as I said, let's say if FBAR basically identified that for this particular type of check which it needed, we need to go deploy a new firmware update, or we actually want to go ahead and update the new kernel, then Cyborg is that low-level code which actually goes and does the actual work of deploying that fix. As you see, all of this is done on off machine. So because there are times where the machine itself could not be accessible, so we might find other ways to kind of get into the machine through other daemons, and all of this process runs off the machine. Finally, once we try all of that, so like, a check finds something, if there was an FBAR remediation deployed, we would try and attempt to it, and if that remediation meant if we would have to we have to go ahead and reboot the machine, or probably like format the drive, do cyborg, and the problem has to go away in one of these steps. And let's say if FBAR failed and cyborg failed, and none of those could actually fix the problem what we were seeing at source, that the final step is actually to go ahead and repair ticket. The point we are trying to make here is also that swapping drives is also extremely expensive for us, and that's not our first default behavior if once we see a problem that we want to just take the drive out. It does cost us a lot to go ahead and do that, apart from just going and yanking the drive out. So it's always our last foolproof method to go ahead and swap the SSD until we really think that there is no other way we could fix it in an automated fashion. So at that point, there's a repair ticket which is created for a DC technician out there in the data center to go ahead and swap the SSD. We would go ahead and capture all the detailed logs which is needed to go further debug this particular issue, and then we would go ahead and do some review about why we see some of these problems in there. Now this happens on a per SSD, so just think about it like if there are like thousands of these which are failing, then the scale of this is massive, because you will just see thousands of tickets which are floating around across every data center in the world, probably for us. And that's where you need all the anomaly detection, where you're going to find out like, oh, what's causing this and how can we prevent more bleeding of these drives in there, because we cannot just go ahead and replace all the drives on day one, but they can start failing all of them in an hour or in a day for some reason or the other. And I can give a classic example here. So one of the issues we were debugging last year was this was a drive which we deployed in our fleet from a vendor A, remains unknown. And what was happening was, in a certain workload conditions, if you actually go ahead and send a combination of large trims in the middle of a certain type of workload which we're sending, this drive would actually go ahead and cause a lot of ASIC hangs onto the drive's controller. Now, it took us a lot of time to go find out that it was a combination of the workload plus this large trims which was causing the drive to actually hang. And we had a large quantity of these drives of this vendor actually deployed in the fleet. Now, this was not happening on every single drive which was on the fleet. It was only happening maybe on 2% of the population. But there's always this worry that till we are debugging this to be an issue, what do you do about all the entire other 98% of population you have in the fleet? So one of the stopgap measures in there, and which is something we hate to do, but we had to do to kind of prevent the large population, was to release a kernel patch which would not send large streams for time being till we actually went ahead and did that. And that's something which was chaotic, but at least could help us survive through the phase till we have the new firmware update to go ahead and update that. But hence, it is very important for us to kind of debug and understand these drives right at the time where we see this failure, because we have to take some actions on the drives which are already in the fleet, even though they have not experienced a failure. But if a population of the same model, same firmware experienced a failure there. Okay, so this is a little bit about just like an overview about the types of failure which we see in our environment. Again, this is not an extensive list, and there is a lot more of types, but I'm just trying to bucket some of the larger buckets and some of the more important issues which we see in the fleet. IO stalls, we're going to talk a lot about it. Venkat is going to dive much deeper into a stall and this problem which we had been facing a lot in the last year, and so I'll leave it up to him to kind of talk about it. Bandwidth reduction. So this would mean like suddenly where we would just see a drop in terms of the overall system bandwidth which we would be getting from, and the result could be because SSDs degraded in performance, or probably they lost certain lanes, or there was some type of throttling which kicked on in some model of SSDs. Could be various reasons why this would happen. Data corruption. We have seen many instances of data corruption in terms of certain workloads triggering file system corruptions to happen. And so these are application level. So you can think about it that at a drive level, let's say if I was using a drive as a boot drive, and the file system was actually using that boot drive to kind of store a lot of its file system critical data, and for some reason the drive aborted a particular read or a write in that, and for some reason that did not end up being a rewrite from the file system. In that case, at an application level, you're going to see data corruption because it expected these file system writes to finish, but they did not finish for some reason or so. and the capacity disabled. So at an application level, again, you would see if a drive has this critical warning turned on, or if the drive is actually reaching into a bad state. You would basically see this drive go offline, but at an application level, what they would see is like, oh, I had X amount of gigs worth of capacity available to me, and suddenly I just don't see that capacity available to me in there. From a fleet monitoring point of view, what that these are problems which the applications don't see, but when we actually collect all this data, which I showed you a couple of slides back, we are able to spot through our analysis and anomaly, we are able to find some of these problems which exist in SSDs through there. So one is endurance. When the drive basically codes, it can actually go to X amount of drive writes per day or terabytes per write per day. I don't know what's the ongoing terminology these days, but it would not basically honor that. So, and you would have much higher write time for a certain type of workloads than what you actually expected for the drive to be. And so we would be wearing drives out much more faster than what we expected it to do. So that's a very common problem which we see in drives, and we can catch it because we continuously monitor the write rate which we are driving to the drive. We also monitor, the amount of physical as well as the host writes which are happening on the drive, so we can come up with the math in terms of if the drive is misbehaving in terms of wearing out faster than what was supposed to. Smart problems. So sometimes there are very few problems which smart can actually help, but it can. So there are some types of types of ECC errors, or it could be the link kind of getting degraded or so. So those are types of the events which we can find through smart in there. Read and write errors. So I kind of talked about some of the D-message logs what we capture. So if there are IO events which basically error out and don't finish or don't complete, then those are some of the events which we try through monitoring to find and catch. Protocol errors, so again, PCI events, if there are link packets which are getting kind of CRC'd, either on the host side or on the drive side, that's something which we always constantly monitor. The best way we feel to do that is probably through the cell logs and through the cell event logs, and we try to capture also the drive side of the PCI counters, but at times, it depends on where the error is. Are you seeing it in the uplink or you're seeing it in the downlink? So it's important to capture these stats on the both sides and then kind of come up with a conclusion of who actually is causing some of these errors to happen in there. So let's talk about some of the debug challenges which we face in here. So kind of like a history in here where we have kind of gone through a significant evolution of flash drives. Like in my 10 plus years of working in the flash industry, we went from like 2.5 inch of SATA drives to the PCI NVMe card to kind of now the even.SSD from the form factors point of view. We have all these cool software enhancements which we are driving to kind of better serve application needs and application requirements with ZNS and streams. And so this SSD is no more like just a simple storage which you just write data to and just forget. It's evolved into a much more complex systems with much more complex needs in there. And we have I remember the first version of NVMe spec which I had reviewed when I used to work with Intel back in my days was like 90 pages were long, and I know Mike's laughing here, but I mean you can kind of see how the number of pages of NVMe has evolved into, and probably what it will in another year. But one of the areas which actually, if you look at this spec, it could be SATA or it could be NVMe, which we have really not evolved as a storage industry, and this is just my opinion. I understand some of you might differ in this, is how we actually debug these drives and how do we make the entire debugging process much more efficient as an industry as a whole. The two big tools which are always told to me is like, what are you talking about? Debugging is so easy. You have telemetry and SMART. Telemetry for hyperscalers is completely encrypted. There is no way we can look at what's going inside the drive. We cannot save the data. It's a binary data which I have to just blindly trust and send it to the vendor. And SMART, I mean, here's what the NVMe SMART log kind of displays in the type of counters. And I just talked about all the types of application level issues which we see in there. How many of those can we actually debug looking at these SMART counters? I think none. So these are the two debug tools what we have in today for hyperscalers to go debug flash drives. So there's a lot of work us as the storage industry needs to do in terms of how we can all efficiently debug flash drives. And also I think exposing some of this data is actually in the interest of both parties, because if you do that, we, as I said, we are capturing a lot of this data on a per day basis on per device in our environment, and we're always very happy to kind of share this data with the vendors to kind of understand how their drives are actually performing in our fleet, just because of the scale advantages. So again, I feel SMART is not really that smart. It really doesn't help us solve or help debug much of the problems. The telemetry solution, what exists in the industry today, is really does not work at scale. As I said, capturing encrypted binaries and sending it to the SSD vendors and debugging and solving that entire model is just not helpful. So even though we have the word called telemetry, it's really not helping solve some of the problems, at least in our infrastructure. And it's a long turnaround for debug. To kind of even get to a first level analysis of an issue, what we see is it takes a much long time. We're talking about months over years sometimes. And as I said, we really have to take immediate action steps on the entire population of a drive as soon as we see a problem happen in an environment. But we're not able to, because we really don't know what's wrong with the drive until sufficient triage and stuff is done. And again, the other problem with telemetry is you cannot be capturing telemetry logs all the time. You have to have a very smart intelligence service which captures the telemetry log. It's a round-robin log. Most of the vendors implement it that way. So if I capture the log like 6 hours after when the issue has happened, it's too late. I've missed all the relevant information. Most of the times what I hear back is, this log didn't see what you are actually reporting the issue with. And that's challenging, because how do you basically time capturing of logs right at the time where the event or the issue happens? So we need to design better logging, and as we kind of go into some of the future slides, we'll talk about that. This is my kind of caricature drawing about how things work at scale. So if you look at it on the left side, you will see like there are these multiple servers which have multiple SSDs in here. The red ones are actually SSDs which somehow through our machine checker or through our alerting we found out are bad drives. And then what over the network, once we find this, we go ahead and pull the logs into an offline server, so that because we have to send them over email or Dropbox or something to the SSD vendors, which again happens at a time which is not at the time where the failure is. These logs are then sent to the SSD vendor for debug, and then sometimes, if you're lucky, it's days. If not, it's months for the debug resolution to come back. I just feel this whole model, the picture itself looks messy, and the model is even more messier when in practice, and it's just not the efficient way how we debug this in there. So that's the point I'm trying to make. Now let's actually try to focus on a real problem. I've been talking about some of the hypotheses of this. I want to give you guys a real example of the latency issues which we see in our fleet. What are the odds of seeing this particular issue? I know most of you might be saying, like, what are you talking about latency? I mean, the SSDs have matured so much, we don't see latencies in the order of seconds and stuff these days. But we have some numbers and data for you guys to kind of show you that. And then how has Facebook or Meta approached to kind of solve this problem at scale in terms of better debugging and resolving this issue. So I'll have my co-presenter Venkat kind of talk about it.
Hey everyone, I'm Venkat, and I'm here to kind of present a particular use case of how we use this debug log that Vinit's been working on, how it helps solve latency problems in particular, and why latency is a very peculiar use case in terms of debug. But before I start to do that, let's kind of baseline on what exactly we mean by a stall, because that would depend on where you're sitting in the stack, and people who are SSD firmware developers may differ from application developers, right? Like latency stall is anything that we define as a single I/O level takes more than expected time to complete. So what is the expected time? Just for reference, we use 1 second here, and that's being generous. So if a single read or a write or a trim takes greater than 1 second, we classify it as a latency stall. And there are a number of reasons why latencies or a stall could occur from the SSD. We've seen different instances of it, like firmware bugs. You might typically think, well, it's probably related to high throughput, right? We've actually seen firmware bugs where the latency or the stall manifests only in low throughput, right? And that was a peculiar bug where the write rate had to be just enough slow for you to kind of queue up back-to-back closure of open blocks. So as you can see, these are incredibly hard to detect. These can be very arcane bugs, right? QoS bugs. And as Vineet alluded to earlier, they're extremely long turnaround time from the time we see the problem to being able to reproduce it to being able to eventually debug, root cause it, and apply the fix to the fleet. In the meanwhile, there could be significant impact to the services, and let's just look at the number of stalls, right? We did a random sampling of how many stalls we see in 1,000 devices. There were 40 distinct SSD stalls being greater than 1 second I/O. So the equivalent odds are the odds of Los Angeles Rams winning the Super Bowl, which they did end up doing last year. So as we can see, this is not like some mythical stuff we're talking about. This is stuff that we encounter in the fleet every day. And for some architectures, this is even more critical. Like this is probably, if you go on the Facebook engineering blog, you'll see how our MySQL, distributed MySQL architecture powers most of our critical applications, right? And what we have here is each server has multiple SSDs, and across these SSDs, we have like different MySQL instances running, each serving a number of client connections, and the storage engine obviously is Myrox, as we pointed on the previous slide. So in this architecture, a single SSD I/O stalling somewhere down in the drive can ripple all the way up to the application layer, and not only can it impact the actual transaction, it can actually have a noisy neighbor effects as well, right? So for these critical applications, so this particular application that I showed you right now, we did a thought experiment, right? So we looked at that particular distributed MySQL database, and then we kind of looked at the number of sorry, this is the pointer. Okay, so we looked at the number of reads that are within 1 millisecond, 10 millisecond, different bins, right? And then we kind of translated it to I/O percentiles. Now, a lot of SSD firmware developers would be looking at this and saying, hey, this is great. I mean, look at your 1 second, that's like more than 6 nines, right? And that's usually the numbers we tout. We say, oh, my 6 9 is like 600 milliseconds, we're good, right? Like, or 5 nines. But this kind of goes on to prove why every single stall matters. Now, remember that the way we calculated this is we look at 1 second interval, and if there was at least one stall in that 1 second interval, we increase the bin by 1, right? And then that's how we arrived at this percentile. So we then translated to percentage. Now, what if we flip this around, and instead of looking at 1 second aggregate, we looked at every single I/O, right? Like, let's say we're doing 4K IOPS, right? Like, so that's 4,000 IOs in a single second. So if you applied this percentile to see how many of those reads, let's say 4K reads, right? Like, how many of those reads are actually going to potentially be stalling because they are masked under the 1 second interval, right? So, well, we see there's more than just one stall, right? Like, and how long does it take to get to a 1 second stall? It just takes like a minute to get to see 4 of these 1 second stalls, right? And just for frame of reference, like the access time of the very first commercial HDD back in 1956 had a seek time of 600 milliseconds, which is roughly what we're looking at, right? So this doesn't take too many IOs to actually start seeing a 1 second stall. Now, what if we go from 1 minute to 3 days, right? Like, so there's a real possibility of us seeing like 10 second stall, like, and just to tell you, like 10 seconds is like more time than Usain Bolt took on his 100 meter sprint world record. So that's really slow for an SSD. Now, luckily for us, not every one of these stalls is fatal, right? As we know, there's caching and there's all sorts of nice things happening on top of the SSD. But when it does hit, it hits us hard. Now, and it hits us hard for 2 reasons. One is depending on how you looked at the previous slide, you could either think that that's a lot of stalls or that's occurring, the intertime arrival between the stalls is too low. So the chance of being able to catch that when you're monitoring from the host side is really low, because you're not going to be it's not efficient to monitor every single IO, and you are going to have to aggregate at some level, whether it's a second or a minute or whatever aggregation it is, right? So it's really something that the drive can do better, and that's why the latency monitoring log spec that Vineet kind of helped push to the OCP committee, we have internally developed tooling around it. And in this particular latency issue, we try to debug by setting 4 latency buckets to get around 5 millisecond, 50 millisecond, half a second, and a 1 second, right? And on the 1 second bin, we actually set it to capture an internal telemetry dump, which we uploaded to our repair service. So with this, we are able to monitor every single IO, and we are able to capture the log, the internal telemetry dump, exactly when the latency stall occurs. And as Vineet mentioned earlier, this particular latency monitoring log is from an actual implementation where we did end up debugging it to the trim, causing the writes to stall. But this could have taken like many months for us to debug without the latency monitoring log. And the latency monitoring counters, now we have 4 buckets right now. Each of these buckets can give us we can tune it in the fleet to get us different histograms. And this data we're trying to feed to our existing pipeline that we have to arrive at more say efficient remediation flows, right? Like, is this something that needs to be swapped or something that's reimaged? We already use a lot of the kernel statistics and workload level metrics and smart counters on top of this dimensional analyzer, and now this is another potential data that we're looking to use. And just in interest of completion, so it's not always the SSD issue, right? And a lot of times, as systems engineer, we are like trying to acquit the SSD from the failure path. So the traditional approach is to look at the workload characteristics using a block trace. As you know, Facebook also is a big contributor to the BPF ecosystem with a lot of the libbpf and BPF trace contributors coming from Facebook. We have a lot of internal tooling that we have developed around BPF that are able to latch on to very specific parts in the stack, like trace down to particular block ranges, look for double completions, or look for timeouts. We're able to kind of make a lot of custom scripts and deploy them at scale very quickly using our managed BPF infrastructure. So this is kind of an overview of how we handle latency, and I want to hand it back to Vineet to kind of talk more about what else we have on the agenda for debug.
Yeah, thanks Venkat for the dive through in the scale. Just one point which I'm trying to which he was trying to describe here, and I'll try to add a couple of context in here is, we as I said, for us it is very important to measure the entire storage stack and not just SSDs. In the interest of the audience, what we've talked about is a case study on, what we look at inside the SSD. This slide kind of shows that we watch the whole stack, and we are trying our best to kind of map every layer in terms of trying to find out where that one read or write request came for, and where in that entire pipeline was the delay or the stall cost. Majority of the times, it's always the SSD in our experience, in our infrastructure, and it's very seldom that it's actually a block layer or a kernel level or an NVMe driver issue which is actually causing a stall to happen in there. I'm not saying that doesn't happen, that still happens, but it's much less of our current chassis. The odds are much lower to even compute versus the ones which we showed you earlier in there. And what you see down over here is actually is a perf trace. So if anyone's using a perf tool or a BPF tool, you could actually deploy and map every single IO and every single trace events happening in each of these layers, and then you can come up with this trace. And you cannot, it's not visible for a reason, but you could actually map each one of those applications and the time which a single event or an IO has spent in that. So we do monitor and continuously do that on both sides of the system in there. So summary, I hope this presentation, what we gave, and the case study, what we solved, and some of the examples, what we gave was adequate to kind of explain that at-scale debug for SSDs is extremely difficult. And I mean, we could talk about many more issues. The latency was one of the ones which actually bit us the most hard in the last couple of years. And just by a very simple design of efficient logs, we could come from resolution to months to like days. So prior to like latency monitoring log information, the same issue took us like around 6 to 8 months with a couple of vendors to go debug that. Benefit of latency is, we could go trigger an event log right at the time where the event happens. So the flash vendors can program that. So we were able to debug that issue from like months to like in just a couple of days because we were able to capture logs right at the source of where it happens. And I'm sure you all understand capturing the time of the log and when you capture the log events is also essential, not just the event, pretty much in there. We have multiple initiatives which are going on in terms of, we would love to basically partner and engage with more industry participants who are working on the BPF scripts and trying to enhance the BPF tool for storage to help solve, not just the flash side of the latency problems, but also on the Linux stack. And we would love to hear your ideas. Latency monitoring spec, the link's probably shared in the presentation, so wherever you guys can download, you'll be able to do that. That's part of the OCP initiative, so we highly encourage and recommend if you're interested, please join the OCP side and try to influence in terms of how can we better debug and better design our drives for debug. The last thing which I did want to mention was about the NVMe CLI plugins and the OCP. So one of the other challenges what we have faced is there are multiple plugins which exist in the storage industry. So if you ever have to go buy a particular drive with a particular vendor, they kind of release their own vendor plugin. So even though we have what we call from the NVMe terminologies, like we have a common telemetry, it's really not common because you have to have a custom a CLI from that vendor. So if you now look at our environment where you buy drives from multiple vendors, you have more than 5 plus, 10 plus kind of plugins which are floating around. Each one of those has to get integrated. Each one of them has to get validated to kind of maintain and sustain with the drives. And the sad part about it is certain plugins are much well designed with the other, but there's no sharing in here. So as an industry, we are kind of stalling each other's by not having a common plugin. Our approach to that was to actually go do the work ourselves. And so we went ahead and came up with an OCP NVMe CLI plugin, so you could actually click on the link and it'll take you to the GitHub, which is an open source custom CLI. And Meta is very interested in terms of pushing the industry towards using that as a common CLI and kind of getting away from these vendor unique as flash vendor based CLI options in there. So you could join in there and kind of look at how we've designed and come and provide feedback if yeah. And as always, we welcome ideas on how we could, we're not here to claim that we probably have the best debug tools and methods available to debug that. We're still learning and kind of figuring this out. So we'd love to partner with industry in terms of how can we better improve our understanding of how we do debug flash devices and storage devices at scale. As I think if we all really put some good focus on this and try to solve this problem, we can make this much easier to debug. A nice analogy to this is, as I said, part of my job is flash, but when I look at other components in the system, if you actually look at the CPU side or the NIC side or probably in the GPU side, the amount of crash terms and debug logs and the way the debug ecosystem, what they have as a component design is so much more advanced in terms of trying to find the real issue. And when I compare storage in comparison with that, I think we're much behind in terms of that. So I think I welcome some of these ideas, and I think we all can work together to make this problem much easier. So thank you. That's my presentation. Questions?
Yep. Yeah, a couple of questions. At the very end there, you mentioned someone has a vector environment for tracking this. I just read that once.
I'm sorry, I couldn't hear you. Can you be a little louder?
At the very end, you mentioned that some environment is much better at tracking these kinds of problems. What was that?
Oh, I didn't mean there is some environment. I just said that, certain other components. So if you look at CPUs or if you look at GPUs and the RAS features and the debug features where they have designed are much more advanced than how storage industry has evolved their debug tools.
Okay, then I have two questions. Are you
Yes.
Or does that fall into the same class of problems as what you're calling telemetry?
It's the same as telemetry. As long as it's not open to us and we don't know what's going inside that log, it's really not helpful.
Right. It's fully architected. Oh yeah, it is yeah, the events are all totally standardized.
Yes, and if those type of logs can be helpful, so if we can add more events to that, which are actually helping solve certain problems which we see in the fleet, then we could actually go ahead and use that and leverage that.
Okay, now I assume you're familiar with the command duration limits that you can find presently in ATA and SCSI.
Yep.
Problem with that, of course, is that if the command takes too long, it's aborted. I assume that's too big a hammer for what you're trying to do.
Yes.
So what if that were instead able to let the command continue to complete, but throw some sort of notification to the host?
Yeah, so we do that, and that's how we come to basically know that there is actually a particular request which has taken a long time to finish. But when you think about it from an application level, right, there are, as I kind of scaled back into that storage level architecture diagram, there are, once an application request comes in, that query, it's a SQL query, right? It's a SQL database, is a huge database, and one database query, if it's large enough, gets split up into multiple smaller queries. And that gets farmed into these many servers which have SSDs in there. And so one single SSD on a system could lead to this at a higher level, a much larger query. That entire query gets stalled because no one's knowing which one it's waiting for in there. So that's where the challenge comes in there.
Okay, so the problem is filtering out exactly which device has the problem.
Exactly.
And that's why I was asking if this per command duration limit could throw it a warning, say, I have a problem right here on this device.
Yeah, and that's totally fine. And we have basically tried these async event notifications and seeing there are performance impacts to that, because when you actually go service that and at scale, that's just not possible for us to do at this point. Where if there are multiple drives firing async events, and what do you do next on those events, and how do you handle that? That's just not a deployable solution for us. Okay, there's many hands raised, but I think he raised the first. But okay, so.
Yeah, so we do have USDT for a lot of the so user space pass through and other implementations, right? So the drive level, sure, still it's LM log, but managed BPF can help. Obviously, there are like performance kind of concerns with USDT compared to using in-kernel instrumentation, trace points or K-probes. So. I think it's going to be kind of public, but I too early for me. But we do have some kind of.
I was curious if you guys have SPDK deployed anywhere.
We don't have SPDK deployed. Yeah.
So you're pretty much kernel-based.
We're kernel-based, yes.
Yep, that's right. Okay, I think Steve raised it before you, but yeah, go ahead, Steve.
So you obviously are doing some discuss with latency monitor that you get added to the OCP 2.0 and the data center spec. So
Yep.
did you learn anything? Do you think you're going to tweak it, change it, modify it?
Uh,
Or are you happy with what you have for now?
There were a couple of like user errors in terms of how we describe the log, but at this point the log has been extremely useful, and not just us, but we've kind of talked to our other hyperscale partners, and they have found it super useful as well. But as so far, I haven't seen things which we are missing out, but pretty open to kind of add more to it if needed. As I said, the first level problem we were trying to solve was is the drive even recognizing a stall happen, and that happens. And when they do recognize, do they have their event dumps saved at the time when they do that? And that's the critical problem which latency monitoring helps solve. I think you guys get it. Yeah, that's a great question. I did not touch that area about how we actually drive device qualification. hoping one of the future conferences that could be our entire topic. This was more of in terms of even some of these problems which I talked like latency stalls. We see it and we catch it even in the device qualifications. But again, we're talking about qualification is again a limited sample size. There's nothing which can replace the scale of production issues pretty much in there. So. Go ahead, Mike. Yeah.
So telemetry was initially put into NVMe to standardize getting the differentiations between the vendor companies and their internal implementations. And then I hear you say we need to standardize that, and I don't see us getting there because of the different architectures that are available there, different technologies or whatnot. And yet you talk about other peripherals having a more maturity thing. We thought about walking away from telemetry and moving it into a standardization as we get maturity on these standard things that we have in SSDs and get away from, talking about telemetry and differentiations there and start separating those two. I don't see us getting rid of telemetry from the standard point of view, but I see us learning more and more common feature capabilities of debugging at scale.
No, that's a great question, and I truly think that we all have to drive towards what you said. In my mind, what we tried to standardize with telemetry is the ability to collect these logs. So you have just a standard command which you can send to collect these logs, but the logs being encrypted by itself is a challenge. Not just from understanding what the issue is, but we are one big issue from a security kind of hammer coming at us in terms of, and I know some of the hyperscalers already do that. They don't let you take the telemetry log outside their data center. So inherently, the way the model is kind of broken in terms of that. So I definitely think what you suggested is something we have been trying to think and kind of look at. Don't have something to announce today, but as probably as we go forward in terms of thinking and maturing this, we would be able to share more in terms of what we're trying to do there. Yeah, go ahead.
So I people we do a lot of same processes going at scale. Our current processes revolve around a lot of proprietary and custom one-off APIs in order to extract the logs of the telemetry and collect them at scale. We're trying to look toward these redfish for collecting some of these as a more standardized manner. But one thing that we're worried about is each time we're doing some debugging, it's a different problem. We have different sets of log requirements, different sets of telemetry requirements. And we're concerned that it's hard to standardize those properly. Have you guys given any thought to is redfish a sufficient or appropriate API for introducing some of these standard telemetry models? Or are you looking to standardize at a different level?
Yeah, to be honest, I'm not really well knowledgeable on Redfish and the power and capabilities what it provides to really comment in there. But on the side of our goal is, as Mike was kind of alluding to, is capturing these logs should be in a standard way. It has to be. There cannot be zillions of APIs existing to pull different telemetry logs and put different things. It's one SSD. You should be able to capture it all what it's needed in one log, and then it's more about how much of this log you kind of share it so that we can basically post process some of the data which we're capturing at scale, and how much do you actually keep it encrypted for debug. At the end, the goal is just one: is once the issue is found, how soon can we actually achieve? And I'm not saying that as soon as the issue is found, we need to solve the issue in the given day, but we actually have to at least root cause why this happened in a given day for us to kind of know what actions we take on all the devices of the same type which are existing in the fleet. So that's where our focus is in there. Just making sure, how are we doing on time? Out of time. Oh, I'm sorry. I'm open and I'll be here, so I would be welcoming any.
You can still do a few more questions because it's super crowded out there.
Okay.
It's starting lunch and it's a little tight, so honestly, this is a good conversation, so if people don't mind.
Awesome.
Plenty of food for everybody, so you're not going to stop. So if you want to just go.
Okay, awesome. More questions. We can take it. Okay, go ahead, please, sir. Yeah.
Have you seen any correlation between when you see Hyperscale and errors coming from the SSD or some load patterns where they get queued up beyond this thing or this combination of reads and writes? Is anything like that, or is that what you're trying to get to?
No, and Venkat can talk more to it, but at a high level, we have tried so many combinations of this. But as I said, all we have available is SMART right now, and SMART is limited. So you have maybe the number of reads, number of writes, and probably the ECC errors, and that's all we have. So we don't see any correlation.
And actually, one of the things we've done is kind of try not to penalize the SSD when it's like high Q depth or high QoS, right? So we do filtering based on utilization. So we only go after those stalls in terms of repair. I mean, there could be other actions you need to do with high, like a workload abusing the SSD. But yeah, we try to pick ones where it shouldn't really be stalling in a remediation flow.
Yeah, or else we would be failing a lot of SSDs. So we try to exactly pick in a low utilization and not the higher utilization because it's expected in a higher utilization for these to happen. But some of these stalls which we talked about are actually happening in a low utilization environment where we don't think it should happen.
Low utilization and low disk usage too. So that's really like a curious kind of thing that we go after. So
Yeah, you first, Igor. Yep, you want to take that?
Sure. If I understand correctly, you're talking about the correlation engine, right? Like, so are we comparing like do we have a good success sample set when we do the correlation, right? Yeah, we do, but the workload part is kind of tricky, but we do understand like what you're alluding to, right? Like it has to be for that particular workload, what is the success? And so that we try to do some of that in the dimensional analyzer. Yeah.
Yeah, so we do have many profile tools available which we capture traces of our workload and try to understand and correlate them. But bear in mind, these workloads are also kind of changing over time. Like before pandemic, we didn't even know we were going to accelerate and build Reels, for instance. And Reels is one of the biggest features which kind of got pushed in the meta, and that changes the whole workload infrastructure in there. And so that would evolve, and then we would come up with our new ones. Yeah, go ahead.
So one of the things we said was like less than 80%. That's an arbitrary one of the specific use cases, right? Like you said, if it's less than 80% in say IOStat or something, right? Like for a window, which means it's probably not saturated. And when it's not saturated, it's probably not because of the workload that we have the stall. So yeah, it's very case by case basis, but broadly 80% is like you could think of one of the things we used in. Okay, so it's 80% IO utilization, right, over a window. So that's kind of how we looked at it. So we said if the SSD wasn't busy, what was at least 80% busy during this time. I know that's obviously missing a lot of nuances of the size and stuff, right? But yeah, at least this gets you like a first level filtering, right? Like, but again, like I said, like you can go more granular, but this does eliminate a lot of those false positives that we may have. So.
Try to pick the no-brainers first and just get them out. So I think Steve raised before you, so I'll let him go first.
Yeah. Many of these latency outliers, I suspect if you ask any SSD designer, do you have a workload that generates a second latency? They go, oh, hell no.
We don't have one. Yeah.
Do you find them replayable, or are they just, you got to debug them in place? And I mean, I guess, but how do you deal with things that are not replayable?
Yeah. You want to answer?
Sure. Yeah, that's really where I think the, like you said, in place kind of telemetry dump is like the best case. A lot of times we've had like vendors kind of tell us what is the exact state machine that leads to it, and vendors come up with the repro script, right? Like wherever it's not been straightforward for us to, obviously we go and we try to narrow down and evolve at a recipe that we can, that's replayable, but I think our best bet most of the time is the telemetry dump and the whatever the drive knows about the internal state at that moment.
I mean, a year back, Steve, it would take us like at least more than a half an hour or an hour after a stall has even happened to realize that a stall actually happened, because it would be the application guys coming and hammering us saying your hardware is actually stally. So we're still evolving in this journey, and basically we are at this point where we can actually at least monitor and identify a stall right at when it happened. But I'm hopefully as we learn more and more in this, we can get to the point where we can not just monitor but also capture the replay thing so that it can be easily reproducible. But it's challenging to do that. Yeah, please go ahead.
You mentioned again how late SMART is, and it's 2022, and it's hard to understand why we're stuck with a few poorly defined numbers. And instead of that nice histogram graph that you have there being provided by a drive. Why can't a
Hyperscalers, yeah.
hyperscalers get together and ask and force the drive vendors, at least one of them, to start providing something like this, let alone a group of
That's what we are trying to do. So the latency monitoring was that effort, and the OCP Cloud Health Log is one of those initiatives. So that's what we're trying to do. But again, I mean, we don't want to just go ahead and design something and just throw it on the vendors to go do that. But it has to be done in a more collaborative manner that us as an industry can sound that it's feasible, and we can find loopholes in our design and something which we can use for a much longer period. So, but we are doing that. Sorry, I didn't get that. What do you say?
OCP can be kind of a solution that's relegated to enterprise vendors who can use that, right? And that kind of leaves the rest of us who have to use standard drives out in the cold.
Yeah.
So in other words, NVMe Express.
Yeah, I mean, as I said, my job is limited to the OCP spec, so I'm trying to push it to the OCP, but NVMe is welcome to learn from it, and you could actually speak for the spec and probably and get it in there, but I cannot comment on that at this point. But
NVMe can only take it if OCP gives them permission to do it.
yeah, that's if no for Ross Stanford, that's probably a Ross level question, and you can reach out to him and do that. I throw all these topics to him, but he gets to deal with it. Sorry, go ahead.
So with the latency monitoring log, I can see that you can get to a quick identification of which drive it is. But there are often problems for latency and performance, which are not necessarily just bucket-based, right? So it is possible that the drive may completely hide it because of the pin size or the distribution. So you have QoS variation, you have other challenges. My question is there something that could be exchanged where the bucket size is, here's the X bucket sizes for the different type of workloads that could be given to the vendors, so we could exercise it on our end?
Oh, you could. So the buckets are actually configurable. So you could set whatever your bucket threshold is probably going to be, and you could set the time interval as well. So that's exactly why the time intervals also have been set up probably in the log for that. So you could completely draft up a nice histogram of what a particular workload and a QoS event has been for that. But there is a hard threshold because we are trying to find the P100 latency event over here. So we have to make it on a per read base or a per write base in there. We've done. Time for lunch. Okay, thanks guys.